I saw you. We were talking about physical versus chemical changes. I believe we got all of that in there. Is that correct? All that was completed. Well, I purposely wanted to get through that a little bit because this is going to take me, we don't have a single period today. It's going to take me a full period. We're going to fill this up real easily because we're going to talk about chemical changes today, and we're going to have a lot to talk about and a lot to demonstrate for you. I'm going to be demonstrating a lot of this stuff. When I show demos, all right, remember there are at least several reasons why I do them. One, obviously, it illustrates what I'm talking about in the notes. I'm going to try to illustrate for you what a chemical change is. Obviously, a new substance is formed, okay? And I will try to show you that. I'm going to react a couple of things together here, and we're going to create new substances. That's going to be one reason. But I'm also going to do the demonstration, partly to show you the new equipment and how to use it. And I'll be doing that on the video as well for anybody who is absent. So you have the names. Remember, I'm going to hold this up in a couple of days, maybe by the end of the week, I think, by Friday, and you'll have to tell me to say what? Exactly. Erlenmeyer flask, right. So you'll have to know these names. Now, don't worry. I am going to give you a paper with all the pictures on it and the names next to it, and I'll tell you which ones you need to study. And before then, you're going to go back into the lab, and you're going to open those drawers, and all that equipment is in there. So you're going to get your hands on it. You're going to get a paper with it. You're going to have a chance to do that. But that's another reason why I'm doing a demonstration. Okay? Reinforce the notes, show you how to use and the names of the equipment, and of course, just to break things up so you don't have to listen to me talking, your hand doesn't fall off from writing so much. Today, for example, you're going to have very little writing to do. You won't fill up more than half of the paper with all the notes you're going to take today. Yet it's going to take me, I told you, it's going to be one of the longer classes. It's going to go right through the bell. All right? Okay, let's go a little further with this definition of a chemical change. Because I'm going to illustrate this when I write all the reactions over here. As a matter of fact, since I'm going to tape this one, I might try writing them actually on here as well. New substances formed, right? How does that happen? I can't have something, remember what law of conservation of matter and energy said, it can't create or destroy matter. So what you do is you rearrange the atoms you had, okay? A new arrangement of atoms happens when you have a chemical change. And I'm going to illustrate that with the equations I'm going to show you as I do each of the demos. For every demonstration I do, for every chemical reaction I take, I do for you, you're going to see me write an equation for it. And I hope what you're going to see there is what makes those new arrangement of atoms, yet no new atoms being formed. That's what makes something a chemical reaction. By the way, reaction is just another name. A chemical reaction is a chemical change of the same thing. All right. Now, how are we going to know when there's a chemical reaction going on? I will tell you in a minute. That's going to be the main part of this class. But before I do, I have one last thing to tell you, which I usually do in your notes. I'm not going to write every possible chemical reaction you can see, because there are literally hundreds of millions. But as I did with physical changes, I don't need to write every physical change you can see. Crumbling a piece of paper, ripping a piece of paper, crushing a stone. All of that's obviously physical. I'm not going to write that down because it's obviously physical. The ones that are not so obvious, like dissolving salt in water, boiling water, freezing, evaporation, condensation, sublimation, which you'll learn what that is, conductivity, magnets. I put those down there because they're the ones you get wrong. So you want to check that. The one thing I find that people get wrong for chemical changes, if I told you, I would hope if I told you, you reacted an acid and a base, you'd know that was a chemical change. But what some people don't realize is that all biological changes are also chemical changes. Everything your body does is a chemical change. Everything your body does is a chemical change. All biological functions. And not just your body, but any living thing. So, like, if I put down on the test, and I will on the test have a section, you can guarantee it's going to say, classify the following as. And by the way, here's how chem's different in bio in a lot of ways. Yes, in bio you might have had define physical and define chemical change, or have to do a matching definitions of that. Here, that will show up. Yes, you're going to have to know what this means. But you're also going to have to apply it. You're also going to have to tell me what makes something a chemical change and how you would know it in the next part underneath this one. All right, and some other things about chemical changes. And you're also going to have to classify. I will give you examples of something, and you tell me, is this chemical or is this physical? So if I gave you an example of tasting something, or smelling something, or digesting something, or healing a wound. All right? Every one of those things I just mentioned, if you're doing it, if your body's doing it, is that a physical or a chemical change? Chemical. Chemical. See, I got a wrong answer already. It's chemical because your body's doing it. It's a biological process. The growing of a plant, photosynthesis, respiration, your breathing, all of that is chemical. I always get that as a mistake. A plant growing, that's physical, right? No. Plant can't grow without chemical changes, and lots of them. Just touching this board is a chemical change, like physically, and you're talking about your body. Now, I don't want you to overthink it. If I say ripping a piece of paper, you say, well, that could be chemical because your fingers have to touch the... No, I'm not talking about ripping a piece of paper. We're assuming you're ripping a piece of paper. But if I'm talking about your bodies, you'll know it, right? And if I'm talking about a plant, you'll know it. If I'm talking about a biological process, it is a chemical change because there are a lot of chemicals, a lot of reactions that have to go on to make you be able to smell the person next to you right now. Not that you want to. Or to taste the person next to you if you want to. I don't think you should do that. Which is why Kyle left, because you all were smelling him. Or you smelled. I forget. I'm just kidding. He didn't really say any of that, by the way. I don't know how he got there, actually. Now you know where he sits? Back of the room. Back of the room. And I got another person in the back of the room. I got another person in the back. There's no room for you people. Running out of room. Anyway, okay. So let's do some examples of some chemical changes, and we will see if you can tell me. Because the first lab, you already got that homework last week. The first lab is going to be on this, evidence of a chemical change. How are you going to know if a physical or a chemical change is going on? First lab we do will be this, guaranteed. Well, the first real lab. We are going to do some safety stuff before then, and like an intro lab, but the first lab is going to count as a lab. It's going to be on this. And your job will be, I will have you guys do, like I'm going to do up here with all the junk I've got up here. I'm going to have you guys doing reactions. In some cases, they will just be physical changes. In some cases, they will be chemical. The first thing you have to do is tell me was that physical or chemical and why. All right. The second thing you have to do, well, first thing is it physical or chemical? The second will be why. What's my evidence of a chemical change? Okay. That's what we want to see. And the way you're going to get to that right now is by doing something. So let me do some chemical changes for you. What I'm going to do is, since I'm doing it on the camera here, I'm going to make it a little bit higher so I can see these. Hopefully. How high do I need this? Yeah, too high. Yeah, close enough. Is that going to get higher or lower? Oh, that's even higher. Right? Somewhere around there. Hopefully you all can see too. All right, I'm going to do a couple of reactions, and I'm going to turn the light on and off, so you're going to be busy today. All right, let's start with a very simple one. I'm going to take, and remember, part of the reason we're doing these, so I can teach you about the equipment. This thing right here. See that? Looks like a big watch glass. Huh? Big contact lens. It is a watch glass. You wouldn't have known that. Who knew that was a watch glass? Nobody. It looks like a big contact lens for a giant. All right. But it's called a watch glass. And if I hold this up on Friday, and I ask what it is, you got to tell me that. You got to write that down on a piece of paper, watch glass. We use it for a couple of things. Today I'm just going to use it to carry out a very simple reaction. In fact, for this very simple reaction, I could probably just use this. Yeah, that shows up there. How close can I get it there? Close enough. Maybe closer. Oh, yeah. Okay. Now I'm going to take some sodium hydrogen carbonate. Ooh, that sounds scary. Put some on there. Don't worry, it's nothing too fancy. It's a white powder. You turn that light on, maybe let's see if it's better with light on. I don't know. You can probably see it at least. Yeah, you can see that. Yeah, close enough. And I'm going to add, by the way, sometimes you get chemicals in containers like this. All right, and all you do is a lot of times it's just easier to open them up and pour the stuff right into the thing like I did. All right, you don't need to use this, which I told you about last week. What do I call this thing? A spatula. Yeah, you're going to use this. I'm going to use it in my next demo, but right now we'll you just pour it right on there. Just put the cap back on. That way you don't have to worry about spilling stuff, because stuff spills out of that very easily. Now, I'm going to add to that something you're going to use in many labs. Probably a third of the labs we do, you're going to use hydrochloric acid. Okay? It's kind of annoying video. Hydrochloric acid. Okay, now watch how you use this thing. I would put my hands like this. Notice it's upside down. And I would grab it like that. And I want to do it like this because if I take this lid off and just put it on the ground, or on the ground, but the table, I'm going to leave a little spot of hydrochloric acid there later on. I can touch that, burn myself. Yes, you are going to use hydrochloric acid this year. You're going to use the burner, which I'm going to light later on. And you're going to use all kinds of chemicals, some of which are very, very dangerous. Some are not. Some are just sugar and salt. I'll tell you why you don't want to eat them either. But obviously you don't want to eat these. So I'm going to take a little of this off of there, and that's how I hold it. You see it again? I never put this down. And I still have a free hand because I've got this facing out. I also don't want to do it this way because now what's going to happen? Any acid that may be on the bottom of that is going to be touching the glass, and my hand will be touching the glass. So I want to hold it like that. That's part of the techniques you're going to have to learn when doing the lab. So let's go back to this guy I'm going to add them together. And you're going to tell me what you see. What is my evidence of a chemical change going on here? Can you see that? What's my evidence of a chemical change? What'd you see happen? I should call on people. I want to learn your names. I don't really want to learn your names. I have to learn. Kyle! That's funny. Austin, what do you think? What'd you see happen? There it is again, in case you missed it. It bubbled. That's it. It bubbled. Turn that light off. It fizzed. Releases a gas. Fizzing. Absolutely. That's one way you'll know there's a chemical change going on. Absolutely. You add two things together and you get a gas out of nowhere for no reason whatsoever, you can be pretty sure that you've got a chemical change going on. Okay? Now, interesting. I want to show you, I told you for each of these, I'm going to do a, I want to show you the equation. I was in the other class because I wasn't videotaping, I did the equations over here. So I'm going to think I think I can do it this way. Watch. If I can get a new board, right? Yeah. Okay. And it's going to be white for the people watching. Not going to be great, but whatever. All right. What did I add together? I added sodium hydrogen carbonate. Okay. So that's do not write this down. No need to. You're eventually going to be within a few months. You're going to be writing these kind of equations and these kind of formulas. You know, left and right, you'll be able to name everything as well. But let's just start out with. Oops, sorry. Let's just start out with. I need that one. NaHCO3. Okay, that's that white powder I added in there. What did I add to it? I added hydrochloric acid, HCl, plus HCl. Now, I start off with this first demo for a couple of reasons. I have to show you something that forms a gas, and that one does. But there's another reason I use this one as my first example. It happens to give me three things that you have already know the formula for. There aren't many things you know the chemical formula for. I would bet you there are only three, maybe four things you know the actual chemical formula for. And I'm going to show you how you're going to get that formula by rearranging these letters and coming up with something you've heard of before, something that you use every day, that you've heard of before. It's a formula for a common substance. Very, very common, as a matter of fact. I'm going to write a little smaller so I can fit it on there. NaHCO3 plus HCl yields. What letters can I put together to make something I've heard of? Who wants to give me a guess of what you can put together? A compound that you know the formula of. There are only three or four. What's one that you would know the compound? The formula. Who's that? What? Sodium chloride. Sodium chloride. What is sodium chloride? Salt. Absolutely. This sodium right here and this chloride right there, okay, they get together and they rearrange. When these guys rearrange, that sodium and that chlorine get together and make salt. Absolutely. There's some other guys left behind. An H, a C, some O's, another H over there. I'm telling you there are three products made. What's another extremely common compound that you're all familiar with and you know? H2O. Let's put him on there. We'll make him red. Probably should have made the water blue. But anyway. H2O. So that's taking this H right here, and this H right there, and one of those O's, right? And I'm making water. Now, raise your hand. Who knows what the last thing is that is going to be made in this case? I'm going to use orange for that guy. Raise your hand. What do you think? Caleb. Exactly. Carbon. And the other two O's I didn't use there gives me CO2. How about that? And that's why I did that. I did this reaction for a reason. It shows me the three guys you're actually familiar with. All right? And it illustrates my evidence of a chemical change. It was fizzing. All right? And it also illustrates something else. Let's talk about this from Thursday or Friday. Thursday, I think, last week. Didn't I talk about the law of conservation of matter and energy? Right? Remember that? Okay. Well, in the law of conservation of matter and energy, what did I say? You can't create or destroy matter or energy. How many NAs, how many sodium atoms, NAs, are on this side of that line? Oops. Of that line. How many NAs are on this side? One. How many are on that side of the line? One. So one sodium atom over there, one sodium, didn't lose any, didn't gain any. How many H's are over here? Two. One there and one there. How many H's are on that side? Two. How many C's are over here? One C. One C. How many O's are over here? Three. How many over there? Three. 2 and 1 is 3. I just illustrated that law as well. Okay? So I've illustrated not only this is a chemical change because I have new substances formed. And when I say new substance, here's what I mean by new substance. I'm going to take this. I'm not going to move the camera for this, but I'm just going to show you guys. And I'm going to dump this acid on my hands. Why am I not screaming in pain right now? What did I just dump on my hand? Salt water. I just dumped salt water on my hand. A lot of people have a hard time with this. They say, but you added acid to that. How come the acid isn't there anymore? The H is still there. The Cl is still there. It just ain't acid. It's salt and water. And you saw the water pour over my hand. If I tasted it, it would have tasted salty. You don't ever taste it. Where did CO2 go? Yeah, the fizzing. That's what the fizzing went. That was the fizzing. That's what caused the release of the gas. Good. All right. Let's get back to this. Now, let's do another one. And again, using some new equipment and doing something a little bit different. This time, I'm going to have to light the burner. Not exactly sure how I'm going to do that without on this thing here. Maybe I can do it. Let's see it. Yeah, you can see the burner. You can see the thing a little bit anyway. Close enough. All right, y'all watching? I'm going to show you how to light the burner. Because you're going to need the burner for this next example. So I grab what's called a striker. That's what this thing is. It's called a striker. Okay? And a striker, don't be afraid of it. It won't hurt you. Those little sparks, not going to hurt you. Okay? People are always afraid of this more than they are of the gas. I'm going to turn the gas on. And by the way, I'm going to illustrate this much better before we do our lab. But I'll show you right now. You turn the gas on by turning this little knob, this little handle, straight out. It is on now. It is off on either side. You see it? See, if you can't see it, you can look in the back. It's on and it's off. Okay? Either side is off, out, straight out is on. So I turn that on. I've got my striker with me. And, of course, you have your goggles on. Now, I got the cool goggles, but you guys are going to have to wear the ones that fit right up against your face. All right? If you call these cool. Turn these on, straight out, put the striker right over the top, one little strike, you get that. All right? That's how you light the burner. Right over the top, just a couple, I'll do it again, see it for the video as well. Right over the top, just make a strike like that when I go to light. Turn it on. There it is. All right? Now, you want to make sure you don't touch any of these things on here. I could adjust the amount of air that's getting in there. If I lower it down, it gets to be a very dirty flame. We don't want that. And I could If I screw it off too much, it's going to fall off. And down here, there's a way to adjust. I don't want you adjusting any of those things. If you turn it on and it's not a blue flame like that, call me over and I'll help you with it. Okay, there's my burner. Okay, and that's how you light it. And yes, you're going to have to do this. Another thing you're going to have to do, I don't have to, because I don't have much anymore, is tie back your hair. All right, those of you who have long hair. Okay. Let me take a test tube, nice, clean, dry test tube, and I'm going to add some sugar to it. Okay. Now, here's where I get my sugar. From the stock room back there, in a bag that Weiss probably hasn't made in about 10 years. Okay. I don't use a lot of sugar. Okay, it's probably been sitting back there next to all those other chemicals, and I'm going to add it into some beaker that you're going to have to use. Okay, so watch. I take some of that, using my spatula, take some of that sugar, and I'm going to add, in this case, to a test tube. I'm doing this for you. I show you where I get this for a reason. Turns out, people, as a joke, like to pretend and like eat stuff. You know, oh, it's only sugar, it's only salt, it's only baking soda. Well, would you eat the sugar out of this? It's been sitting in the stock room for about 10 years, probably around all the cockroaches and, you know, other chemicals, not to mention. I would. Why don't you just roll your chicken patty around on the floor a while? See what you get. I think they do that anyway. Because where else do those little black things come from? I shouldn't say that. I'm going to get in trouble with the cafeteria ladies. All right. This is called a test tube holder. Great name. And you use it to? Oh, a test tube, yeah. But it really is. And the thing is, the reason I actually have to say that, and it's a very good chance I'll hold this up on Friday and say, what is this? Is that there are other things that kind of look like test tube holders. There's pinch clamps, there's tongs, there's crucible tongs, and there's beaker tongs. And you got to know which one to use which for. You don't use a crucible tong to hold this. You use a test tube holder to hold this. Part of the reason we do a lab safety thing is that, and part of that lab safety thing is naming the equipment. You got to know what the equipment's used for. Okay? Now, watch how I heat this guy up, and then watch for my evidence of the chemical change. You ready? I'm going to put this into the flame. I'm going to heat it gently. At first. You never put something right in that's cold. It could crack, even the Pyrex one that this is. I want to heat this up gently. And notice I'm not pointing it at anyone, not even Kyle, who's not here. I'm pointing this away from everybody, including myself. Because a lot of times you can get a very superheated little spot there, a bubble, and go shooting out. I've seen it happen many times. Not usually with sugar. All right, what's my evidence of the chemical change happening here? Well, if you take a look, what's already happening up here? Yeah, so gas, again, is being released, right, which we didn't expect. Okay, well, we expected it, but, you know. So that's the same. What else, as you can watch here, happening? Yeah, we're getting a color change, exactly. And you can see, actually, it's not just a color change, it's even changing phase. It was a solid, and look at it now. I'm, like, melting it, and it's burning, right? Getting it so hot it's burning. You can see that gas being released. But the thing I'm pointing out to you now isn't the release of the gas. We already saw that. Now walk around with this. You obviously can't pass it around. But I want to, what else do you do? What else do you smell? Yeah, it smells like burnt marshmallow, which is a great smell. Or cotton candy, whatever. Some people say cotton candy. Yeah, it's a good smell. All right, we're going to talk about this guy. I'm going to write the equation out for him. But as you all noticed, absolutely, B is, I'll shut this guy off here. And I'll turn him back around. B is color change. Second way you know a chemical change is going on around here is there's a color change. All right? Now, I want to stop here for a second. I am going to write that equation down in a second. I'm going to put it back on the air board. But before I do, I want to say something about this. Neither of those are written in stone in that respect. In the respect that is every single color change going to be evidence of the chemical change. If I take yellow food coloring and blue food coloring and I mix them together and I get green food coloring, is that a chemical change? No. All right, yellow and blue make green is not a chemical change. Same thing is true for every gas. A gas that's unexpected from taking two solids or two liquids or a liquid and a solid, all right, that's evidence of a chemical change. But where else could you think of something that would also look like it's giving off a gas, but it really is just a physical change? Can you think of something like that? We talked about it just a little while ago. water boiling. I heard both of those together. That's exactly right. Boiling water is a phase change, and it is not evidence of a chemical change. Even though you see steam coming off of it, that's not a chemical change. So it has to be something kind of unexpected. If I put yellow and blue together and get green, that's totally expected, right? But if I did that, I just add a white powder, I heat it up and turn black, that is evidence of a chemical change. Okay. Now, I said I wanted to go to the equation for this guy. So I'm going to need the equation for every one of these. Oh, I know. Okay. That's not good. There. All right. What I told you there were probably about 4 things you knew the equations for. 3 or 4. I already got salt, water, and carbon dioxide. There's only one left, and I just used it. Sugar. What is the formula, you think, for, we'll say glucose instead of sucrose, which is what that is. What is glucose's formula? Come on, from biology, you all know it. C6, H12O6. Exactly. And that's what we took. You don't have to copy it. We took this white C6H12O6 that turned into this black goo. And if you look real closely on here, right on top, turn the light on for a second. Okay, you can see condensation all around there. And you see this is kind of like a liquid down there too, but there's lots of condensation on there. All right, what do you think that condensation probably is? How can I rearrange these letters? You can turn it off again. How can I rearrange these letters and get a formula for something you all know? What is it? Water. Condensation is basically just another name for water. All right, when you see it like that on the window. Where does that leave? What else does that leave that I didn't use already? H and O I used. What do you think? And does it make sense that that black stuff might just be carbon? Yeah. We think of carbon. What do you think? You think of something black, don't you? All right. Now, in reality, I'm cheating a little bit, no doubt about it. Really, when you burn a hydrocarbon, you're going to get 2 main things. You're going to get carbon dioxide and water. All right? But basically, you can see in this case, I didn't have enough oxygen around to do it, so I got carbon, too. All right? Now, let's balance this equation. Because right now, I violated a very important law of conservation of matter and energy. Didn't I tell you that was a law? I cannot create or destroy matter. If I leave this equation as it is, I violated that very first law I told you. 1 carbon, where'd the other 5 go? 12 hydrogens, only 2 over here. So you know what you do? You do. Yeah, we got to balance this equation. You know what I would have to put in front of the carbon? What do you think? A 6. And what would I have to put in front of water? A 6, right? Because 6 times 2 is how many H's now? 12. And 6 times 1 is 6 O's. Perfect. That's exactly what you get from burning water. Actually, and I said I'm cheating a little bit. In reality, aren't you burning sugar right now? One difference. What are you taking in as well? Same black tea, it's not really a difference. You took some of that in too here. What are you also taking in? Oxygen. Don't you need oxygen to survive, right? And if I have those other oxygen, oh, look at this. If I put them right there, what do I get? Isn't that neat? You see? I'm cheating a little bit, but for the most part, that's what happens when I decompose sugar into carbon and water. In reality, I'm really adding oxygen on this side and getting those carbon dioxide, not just carbon. But it makes it easier to see it this way. All right, let me erase this part here. All right. Once again, I saw a rearrangement of the atoms. That is key. I want you to go back here. Okay? Let's go back. I said I'd be talking about a couple of things here today. A new substance is formed in a chemical change, and there's a new arrangement of atoms. Okay? No new atoms are formed. I'm not creating or destroying them. I'm going over all that for you. Okay? Now, let's do another demo. How much time I have? 10 minutes? All right, I gotta have to hurry. Let's check this guy out. Turn the light on again. I'm going to add 2 chemicals together. 2 chemicals that you are probably not very familiar with. Well, one of them you're not, anyway. One of them is salt water. The other one's silver nitrate. Here's the silver nitrate. Now, the silver nitrate is in a brown bottle. You should use that to remind you that it's going to turn your skin brown if it gets on. Okay? I'll pour some of that silver nitrate in here. You'll see that he's actually a clear liquid. He's Silver nitrate itself is not a liquid. Silver nitrate is a solid. So why is this a liquid? Same reason this is. What is this? Salt water. Just salt dissolved in water. This, if you were to look at silver nitrate, pure, solid silver nitrate, would look kind of like salt. Be a white crystal. Salt is a white crystal. I dissolved it in water just like I dissolved this one in water. When I add the two together, watch what happens. What's my evidence of the chemical change? And you got to look carefully this time. As a matter of fact, I don't have a bigger one. Yes, I do. I'll pour it into a larger one so you can see it a little bit better when I pass it around. Watch what happens when I add the two guys together. Okay? Add these two guys together, and what's my evidence of a chemical change? I'm going to pass this one around. People in front won't see it as much. What's the first obvious evidence again? Yeah, we already saw that. Color change. Don't spill it. Pass it around. It certainly looks different for two reasons. One is there is a color change. No doubt about that. There is a color change. But if you just write down color change on the lab day, you are not going to get full credit. Because that's not all that happened. And by the time it gets to the other end of this class, you're going to realize something else happened there. Maybe by now you can even see it. Something called a precipitate. What is a precipitate? Well, it's what most of you can see now at this point when it's being traveled around. What does it look like at the bottom now? Can you see that? Yeah. Can you see the solid at the bottom? Yeah. That is what a precipitate is. As I keep passing it, but write this down for your definition. A precipitate is an insoluble solid formed from two clear solutions. You are going to see that in one of the labs. You do see that, you will write that down, and you will be specific about it. You will not just say there was a color change. There are two problems with describing that in the lab as a color change. Who can give me one of the problems with describing that in the lab as a color change? What's one problem with that? I didn't say what color it changed from and to. Very good. And the other problem with that is you also had a precipitate form, and you didn't say that. So that's why you've got to be very specific in observations. You guys will learn after a while how to do that. Okay? But that is a precipitate. That is a fourth way you would know there's a chemical change going on here. Now the last way you'll know, and let's see actual time this is over, 49. Okay. I still got 9 minutes, that's good. The last way you'll know will be, and this is kind of the biggest one. I'm going to need my books for this one. Show you. I don't want you to write this one down. First of all, mainly because, well, what do I have here? Turn that light on. Yeah, it's bananas. I was hungry. I actually did eat part of these. Kind of gross. But I was hungry. So those are my bananas. But there's something else in between those bananas. I don't know if you can see it. I have this as high as I can with the camera here, but there's a clock, a little digital clock there. Now, let me plug in my banana. Okay? There we go. What happened to the clock? Yeah, the clock turned. What time is it? 1 o'clock. Yep. So what's my evidence? What runs through these wires that makes a clock run? Electricity. Now, don't write that down. Electricity would be an example of a chemical change. Okay? It would be an example of evidence of a chemical change. But I want to find more of a catch-all phrase. By the way, people are always wondering, like, and you're going to learn about this in Chem 2 at AP Chem. The bananas are powering the clock? This is my 2-banana clock, but it's not really powered by the bananas. If you were to look closely, you would find that one of these guys is copper, and the other one is zinc. And I have them reversed over here. I have a copper and a zinc over there too. And what I've really made is a battery. And the banana's not really important. He's just, I could do this with 2 solutions of anything that would conduct electricity. Anything. All right, it would still work. Okay, as long as it can get from here to the electrons can get from there to there, electricity can get from there to there. The banana, it could be a potato, it could be an orange. Okay, it could be anything that would conduct, anything with salt water that would conduct a current. All right, it's the fact that this is zinc and that is copper. Remember, let's do a cell. What kind of battery? Copper top battery. Ever hear that? Okay, it's the fact that you have zinc and copper in this battery that make it a battery, not the fact that it's a banana. You could put a banana inside your copper top battery, I suppose, but you're probably not going to want to do that because it's kind of gross. It wouldn't last very long. However, a monkey would like it, and it would have lots of potassium. All right, I have another one here. Check this one out. Here. What do I do with the areas? I think this is about the right height. Yeah, close enough. I have a little magnetic pill. I put him on there. See this? And I turn him on. Well, that's fun. What good is it? What could I use this for? No, I won't. Actually, that's a good point. This is a physical or chemical change. A magnet spinning around would just be a physical change. What could I use this for to do something in my everyday labs? Yeah, absolutely. I can use it to mix things. Put my pill right in there, right? And now when I turn it on, it spins inside the glass and it makes a little tornado. Isn't that cool? Oh, hold on. Okay. Can y'all see that? All right. Now, it's going to be hard to see this next one, but we'll try hopefully to do this. That's not my evidence of a chemical change. Still, a tornado stirring water is not evidence of a chemical change, right? Okay. What is? Well, let me take some of this. Oh, and I need something else. Give me a second. Didn't know there was going to be a tornado in Burke today. All right. Meet this stupid Tom Clark. Tornado in Burke. Touchdown in Burke. A touchdown right here. I got the evidence. All right. Turn off both lights for me this time. And let me All right. Check this out. Ready? Woo. Can you see it? If you can't, stand up. What's it doing? What's it giving off? It's a color change, obviously, but what's it actually giving off? Can you see? Light. Yeah, light. Exactly. I'll make it a little bit brighter. I dumped the whole thing. Look at that. Woo! That was great. Okay. And then it goes away quicker, though. That was bright, though. All right. So I have, as evidence of a chemical change, you can put that backlight on. We see how dull this actually is. See? You can't even see it. Isn't that crazy? That's why you got to have all the lights on. It's not very great. It's the same stuff they use in glow sticks. Okay? I'll turn that off. And to get that pill out of there, I don't want to stick my hand in there, so look what I got. I've got a little magnet on a stick. It's a magnet on a stick. You stick that in there, and look, it takes it right out of there. And I'm going to rinse them off. Rinse my magnet on a stick off. And put them down. Okay, now I can look what's down my drain. Because it lights up the drain. Okay. So, I can have electricity given off. I can have light given off. Tomorrow, I'm going to do 2 more demos. No, I'm not done. I'm going to write this one in here. Tomorrow, I'm going to have 2 more demos that are going to do. You're going to have something else given off. What heat? Well, I'll spoil the surprise. Heat's going to be one of them. What can I have given? What's a generic form for all those things? A generic name for all those things? Energy. That's the word I'm looking for. Yeah. If energy is absorbed or released. Oh, by the way, did I give you? I did give you the definition of this, right? If energy is absorbed or released, you've got evidence of a chemical change. And I'm going to talk about how energy can be absorbed or released tomorrow. Now, I'm not going to talk about how. I'm going to break it down and graph it out and everything else and call them different names. Anybody know what that's called when energy is released or absorbed? Hint ahead for tomorrow. Begins with an E, both of them. Both begin with an E. Somebody knows. Oh, well, we have to wait a little more then. Can't tell you it now. All right, there's no, is there homework? I think there is. Yes, there is. It's homework. Copy this down real quickly before you leave. But obviously, there's not going to be any time to do it today. We have a single period. Tomorrow, we will actually do the homework. I have some time to do it anyway. Anything that you're going to do, as long as this video is working, which I'm not sure it's going to be, but if it is, I'll have the homework that'll be up there. All right, so you'll show up there. There's not going to be any handouts. The stuff we're going to be doing is a lot of it's going to be lab-oriented, so you're not going to have really a chance to do that. In here, you'll have to kind of make it. Where's everybody going? Who is? Field hockey. Okay, so that's all the people are going to be on. Try to keep up by watching the videos, assuming they're actually online. Right now, it's spinning around with a circle and not doing much. So I'm not sure if this is actually done. More to go.
Thank you. Sorry.
Yeah, you would. Are you?
You're walking home, and then you get the
I have your attention, please, all seniors, please report to the auditorium to vote for homecoming court. Again, all seniors, please report to the auditorium to vote for homecoming court. Thank you.
Fuck you.